Let me first thank the organizers for asking me to give a talk here. I was originally planning to give a very different talk, something relevant to this conference, but now I want to talk on something which is far away from the main subject of the conference, on the congruence subgroup problem. The reason was that I thought I had a new proof of Ratner's theorem, which in the co-compact case, when gamma is co-compact, but unfortunately, there's a gap which I was unable to fill before I came here. So I decided, and since Anish kind of insisted that I give some talk, I said, okay, I will talk on the congruence subgroup problem, which is, I mean, I've been working on at that in the recent past, so we'll talk about that. Okay, let me first, this is a little far away from the interest of most people here. It's of peripheral interest, I suppose. And so I will start with explaining what the problem is first. Okay. See, way back in the turn of the last century, Freakin and Klein. So let me first write down the title. Let's look at the group SL2Z. Freakin and Klein discovered that SL2Z has certain subgroups of finite index other than standard ones. What do I mean by standard ones? A subgroup gamma SL2Z is a congruence subgroup if it contains a subgroup of the form all elements congruent to 1 modulo A, where A is a non-zero ideal. In Z. This was the Freakin Klein. So they showed, in fact, discovered sorry? Sorry, yes, yeah. Thank you. All integral matrices which are congruent to one, the identity matrix modulo A, discovered there exists subgroups of finite index which are not congruent subgroups. This was, it's not difficult to see that such a thing happens, such subgroups exist. In fact, you can exhibit, take a SL2Z, first of all, as subgroups of finite index which are free. And free groups have practically any finite group as a quotient. And then if you choose the finite group other than SL2 of Z mod P, groups of that kind, you can easily see that it won't be, the subgroup will not be a congruent subgroup. That's the way it works. Anyway, so, and then this question was really forgotten for a long, long time, till the early 60s or maybe late 50s. There was a discovery made by Bass Lazard-Serre and independently Winnicke through the following theorem. In SL and Z, n greater than or equal to 3, every subgroup of finite index is a congruent subgroup. So the situation becomes very different the moment n is greater than or equal to 3. And this triggered off a series of questions, and the general problem was formulated by Serre. Formulate the problem in the following fashion. Let G be a linear algebraic group over K over a number field K and S a finite set of valuations of K containing all the Archimedean valuations. Let OS be the ring of integers, ring of S integers in K. In the case when K equal to Q, this simply means S is a finite set of primes, and you just invert the primes in S. OS is the ring of integers in K. And consider now G assumes the linear algebraic group defined over number field. So G is contained in GLN. It's a C. It's defined over K means G is the set of zeros. Algebraic group is a set of zeros of functions of the form P xij determinant xij inverse P a polynomial P is a set of polynomials P in a set of polynomials with coefficients in K. So when I say an algebraic group defined over K, I mean a subgroup of GL and C, which is also the set of zeros of a bunch of functions, which are all polynomials in the matrix entries, together with the determinant xij inverted, polynomials in that, and the coefficients of the polynomial should be in K. So that's what an algebraic group is. And then I can talk of GOS, which is simply G, C, the C points of G, intersection GLN OS. Then the question is every subgroup given a subgroup of GLN OS a finite index, does it exist an ideal A not equal to 0 in OS such that subgroup gamma is that gamma contains all G intersection in GOS, G congruent to 1 mod this ideal. So that is the problem. Given any subgroup of finite index, in the integral points of G, the integral points of G make sense because G is already contained in GLN. The only thing is that, the reason that you should assume it's defined over K, unless it's defined over K, this group may even become trivial. And there will be no interest in it, whatever. If you want this group to be reasonably large, you have to assume that G is defined over K. So this is the question. The special case when G is SL2 is the question which was answered by Freakin and Klein. And for n greater than or equal to 3, the question is answered in the affirmative, as I said, by Serre, Bass Lazard-Serre on the one hand and Menike on the other. And then Serre went on to formulate the question in this fashion. And then he also had a way of, suppose it fails, how do you measure the extent to which it fails? He did the following for this. So let us look at the group GOS. You can topologize it in 2 different ways. One is to declare the set of all subgroups of finite index as a fundamental system of neighborhoods of the identity. That will make it into a topological group, and then you can take its completion. So which is nothing but the profinite completion of GOS. So let us denote by G hat OS is the profinite completion of GOS. Let me denote by G bar OS, what I call the congruence completion. This is the completion when you take the subgroups of congruent subgroups as if it's a fundamental system of neighborhoods of identity. It's a, if you like, it's a smaller family than the family of all finite groups, of subgroups of finite index, and you form the projective limit of G modulo the congruence groups. So GOS is the projective limit gamma congruence group G mod gamma. Then obviously the topology here is coarser than the topology here, therefore get natural map G hat OS G bar OS. It is clear that this is subjective because both are compact groups and GOS is dense in G bar OS by the very definition of completion. So the congruence subgroup problem, if you like, is the determination of this kernel. Kernel pi, which I denote CSG. The point is that although in the definition, integral points make an appearance, and the integral points will depend on the way G sits inside GL and C. If you take a conjugate of G by a rational point in GL and by a point in GL and K, you'll get another group. The integral points may be different. But it turns out that the kernel here, CSG, is independent of the choice of the rational points. In fact, another way can be reformulated the following. The system of congruence subgroups gives a structure of a topological group on GK itself, makes this into a topological group, GK. But what you would do is to taking them, the congruence subgroups, as a fundamental system of neighborhoods of the identity. One in GK. That gives you topology, and you can complete GK with respect to this topology, taking the left uniform structure. You can also do it with the right uniform structure. It turns out there's a canonical identification between the left uniform structure and the completions of the left uniform structure and the right uniform structure. So those are technical points, but anyway, you can talk of the completion of GK with respect to this family. And similarly, you can talk of this GK with respect to the family of subgroups of finite index in GOS. In fact, one makes the following definition: a subgroup gamma in GK is an arithmetic subgroup if gamma intersection GOS has finite index in both gamma and GOS. Now, one says that this is also said in a different way. You would say that gamma is commensurable with GOS. So, get another topology. Let me call this structural topology group. Okay, get another topology on GK. We denote completion of GK with respect to this topology by G hat K. And here, the completion with respect to topology, again, completion with respect to the congruence subgroup topology, I denoted G bar K. In fact, one should put an S. I'm talking about, sorry. When I say congruence groups, it all depends on S. I'm taking S integers. So I should probably say here, system of S congruence groups. And similarly here, yeah. And the completion, therefore, I should put GS bar K, similarly G hat S K. So, in other words, one declares a set of all arithmetic groups as a fundamental system of neighborhoods of identity in GK, S arithmetic groups. S arithmetic group. I will often omit saying yes because I'm fixing yes once for all. Yeah. Sorry?
Same as the profinite completion?
No, profinite doesn't make sense because these are not subgroups of finite index of GK. They are only subgroups of finite index in GOS. What happens is this: turns out if G, GK is contained in the group GAS, where AS is the group of, is the ring of yesterdays. That is, you form the various completions of K at various valuations other than those in S and form the product. You get this restricted product, you get a group which you call GAS, and GK is obviously contained in GAS. The congruence topology is nothing but the induced topology from this. Topology, S congruence topology on GK is induced topology from GAS. And what I call GK bar is nothing but closure of GK GAS. One makes a distinction between these two because GK in general is not dense in GAS. What is true is, if G is simply connected, which is same thing as saying the complex points as the Lie group is simply connected, G is simply connected, it turns out that GK bar equals GAS, provided if the GK V is not compact for some V in S. That's the so-called strong approximation theorem for semi-simple groups. This is known. Sorry?
Why did you assume that you contain all the Archimedean valuations?
See, yeah, the ring of integers, the definition of ring of integers. What do you mean by the ring of integers? You just take those numbers in K which are integers in every periodic valuation, which will make sense only for infinite, if you omit infinity, if you outside infinity. So outside, yes, you want it to make sense, so the infinity is included. Okay, so that is so it turns out that the kernel GK hat to GK bar, G bar K is same as kernel G hat OS G bar OS, which is why this notation CSG is justified. CSG is said as a kernel of this, depends only on the algebraic group G over K, and this set, yes, and does not depend on the way G sits inside JL and C. So, the formulation, as I said, is determine CSG. Now, every algebraic group or number field K has a structure. There's a structure theorem which tells you that it's always a, let's assume it's connected. Take a connected algebraic group. It's always a semi-direct product of what is called a reductive group and times a unipotent group. Okay. And so G always we write m times RUG m reductive, and RUG is unipotent radical. G. Now, when G is unipotent, first let me explain. If G naught is the identity connected component, of G, then it's easy to see CSG is same as CSG naught. First of all, G naught is defined over K, and turns out that CSG equals CSG naught. It's easy to see this. Secondly, in this context of the semi-direct product, CSG is isomorphic to CSM times CSU. Actually, it's even a direct product, but anyway, you can write the CSM times CSUs, it turns out. And M is reductive, U is unipotent. Thirdly, if G is unipotent, CSG is trivial. In other words, for unipotent groups, the congruence subgroup property was that every subgroup of finite index in UOS is if GOS is a congruent subgroup. It's quite easy to prove. It's a standard method is used induction. You write the unipotent group as a successive semi-direct product of a one-parameter group and the given group, then turns out you get it right. You apply this, writing U as a semi-direct product. This is in general true for a semi-direct product, but I wrote it only in the case of m times RUG, but it's true for a semi-direct product, and then you find CSG is trivial. And somewhat less trivial is the fact that if G is a torus, then CSG is trivial. This is a theorem due to Chevalier. Here, for the first time, some non-trivial number theory enters the picture. He uses some class field theory to prove this fact. When G is a torus, what do you mean by what does it mean to say G is a torus? This means G is isomorphic to GL1 over R over C, not over the field K, but when you go to the algebraic closure, algebraically closed field C, then G becomes isomorphic to some GL1 power R. Then you call it a torus. So G torus means this. So for tori it's true, and then as I said, G in general is m times m. G is m times RUG, where m is reductive. This means that is m is of the form. I'm assuming G connected in any case. M is of the form some torus T times the semi-simple group. What should I call the semi-simple group? H. Say T a torus, H semi-simple, semi-simple, and T intersection H finite central. It's an almost direct product. That's the situation. So to get it, to determine CSM, you can more or less get all the information about CSM if you know independently what happens to CST and CSH. So can get information on CSM from CST and CSH. All of which says the final problem really reduces to the case when H is semi-simple. So the main problem is in the case when M is semi-simple. Here again, M is semi-simple connected. Here again, you have natural mapping, which has a kernel C, which is, or maybe I should call it mu. Mu is central and finite. And M tilde simply connected. One has an exact sequence like this, and if you knew CSM tilde from this exact sequence, you can get considerable amount of information about CSM. What you can say about CSM is a little more, it's somewhat delicate to give the correct relationship, but it can be done. So finally, what I want to say is it reduces the problem to the case when you have CSM tilde. So problem reduces the case G connected, semi-simple, and simply connected. Sorry? Yeah, from this exact sequence, you can write down a sequence for the corresponding CS M tilde, CS M, and so on. You can relate the two. CS mu turns out to be trivial, but there will be a co-kernel which is not completely easy to describe, but it can be done. That's all I'm saying. So, sorry?
If the center is infinite, say Z.
No, center infinite does not arise in the case of semi-simple groups. If M is any semi-simple group with the universal covering is automatically no, universal covering is finite covering.
Oh, no, but you're taking SL2R also.
No, SL2Z. The condition is on the complex group. Okay. Algebraic group means complex numbers. So the statement is about complex things. G connected, semi-simple, and simply connected. So one can essentially reduce the problem to this further case. That's all I'm saying. It requires a little more work to, you can determine what this is using what this is, using this exact sequence. But if you write down the exact sequence, it turns out you get some Galois cohomology involvement here. But that can't be done. That's all I want to say. So the final problem is only for the case when G is simply connected, semi-simple.
Also simple?
You can also make it simple further. See, the problem is since when you take a group over number field, it may not be, when you go to the complex numbers, it may not be simple. So what do you mean by simple? You can actually assume that even going to complex numbers, it is simple by a certain trick which is known as Weyl restriction of scalars. It can be done, okay? So I'm further going to assume that G is connected, semi-simple, simply connected, and has no proper connected normal subgroups, even over the algebraic closure. Further reduction, finally, further reduction. G is what they call absolutely, this is terminology introduced by almost simple. This means GC is simple modulo its center. The only normal subgroups or the whole group are finite central subgroups. So that's absolutely almost simple. That's the terminology. Okay, so I spent half an hour telling you first reducing the problem to the case, the simply connected case. And then Serre also went ahead and suggested a way of attack on the problem as a whole. What he did was, he said, he first says, let's look at G hat K, G bar K. This is easily seen to be surjective, and you have the kernel CSG. Now, the initial method of proof for the Bass Lazard-Serre method for SL3Z onwards was to prove that this CSG is central in G hat K. Once it is central in G hat K, it's a matter of an extension of this group, which is essentially the ideal group. So this is same thing as, because G is simply connected and so-called strong approximation holds, this turns out to, the closure is nothing but G at S. So what you have is these are locally compact groups. You're looking at a central extension of a locally compact group by some compact group. This is compact because it is the profinite, it's a closed subgroup of a profinite group. So this is compact. You're looking at an extension of a certain locally compact group by a compact group. If I knew it is central, such things are classified by second cohomology. So the statement is, so in 2 steps. Step 1, in good cases, CSG is central in G hat K. And then the problem is determining this central extension, and it turns out what happens is CSG, it turns out, is isomorphic to Pontryagin dual of H2 of G bar K Q by Z to H2 GK Q by Z. This is the second cohomology of this locally compact group with coefficient Q by Z based on continuous cochains. The usual cohomology is based on simply treat this as a discrete group and to look at cochains, GK as a discrete group, and look at this second cohomology by looking at all cochains, 2 cochains, cocycles, and so on. Here you do the same thing, except that you demand that you look only at continuous cochains. So it turns out, once you have this, in good cases, it becomes central, and once it's central, I can say CSG is nothing but the Pontryagin dual of this kernel. So you want to prove that in good cases it's actually central, and then it turns out to be a calculation of second cohomology. Okay. Now, plenty of work has been done on all these things. In particular, for this, for example, H2 G bar K to H Q by Z to H2 GK Q by Z, one notes that the kernel is necessarily a subgroup of the roots of unity in K. Turns out that this is isomorphic. So kernel H2 GK Q by Z to H2 GK G bar K. It's isomorphic to mu K. Actually, one knows that it's either mu K or trivial. Mu K being roots of unity in K. Okay, that's the, as far as the second part, this is due to myself and Gopal Prasad and Prasad Rapinchuk. We did it in many cases and it's complemented by Prasad Rapinchuk, who covered the cases which were left out. So this is the kind of result that one has for the second cohomology. This is out and out number theoretical. Basically, it uses the Brouatitz theory, and for computing cohomology, if you have a space, if you have a group operating on a space, that always helps in computing cohomology. And the group GK operates on, GK bar operates on product of its Brouatitz complexes and so on. So that is the way it's done. So that's one aspect. The other aspect is to prove the centrality in good cases. What do I mean good cases? Serre conjectures following. If sigma V in S, KV rank G is greater than or equal to 2, and I'll explain what these terms are, and if and G is isotropic at all V in S. Minus the Archimedean places. These are the Archimedean valuations. If these two conditions are satisfied, then CSG is finite, is finite, is what he conjectures. And if you prove that CSG is central, then this second result here takes over. So one expects that you can determine the thing whenever this condition is satisfied. You can expect to prove that CSG is central. And this is what has been done in most cases where some affirmative results have been obtained. So, okay, so now let me describe results. Yeah, I have not explained the terminology here. If G is an algebraic group over K, G an algebraic group over K is a split torus. The K split torus if G is isomorphic to product of GL1 R copies over K. A group, I said a torus, I've already said if it's isomorphic to GL1 per R over complex numbers. Here I demand over K itself, it be isomorphic to GL1 per R. For example, if you look at a group like SO2, taking the quadratic form x square plus y square, it's, if you take the group which lives in that quadratic form, you get a group over real numbers because x square plus y square is the quadratic form over real numbers. You get a group over real numbers. But it's not split over real numbers. It splits over complex numbers. So it's a torus. The corresponding SO2 is a torus but not a split torus. So if G is an algebraic group over K, a K split torus is this. So here one demands that the KB's rank, the rank of G is the dimension of maximal K split torus. It turns out all maximal K split tori are conjugates, have the same dimension, and that dimension is called the rank of the group. So what you demand here is that the sigma KB rank greater than 2, and these conditions also seem to be kind of necessary, that it's isotropic at all V. The notion of isotropic. G is isotropic over K if K rank G is greater than or equal to 1. If the K rank is 0, you call it anisotropic. That is, it has no split tori, non-trivial split tori, then you call it anisotropic. This is isotropic over K. So these are the conditions where you can expect CSG to be finite. In fact, in all cases, it is known where CSG is known to be finite. It's already one proves it's central. And then one applies this cohomology theorem, then you conclude. In fact, you have more very precise information. It's either roots of unity or identity. So in most cases, notice that SL2 is a case of rank 1 group. So this condition is not satisfied. The moment you go to SL3, obviously this condition is satisfied. The diagonals in SL3 or higher dimension are of dimension at least 2. In SLN, it's of dimension n minus 1. So the rank is always greater than 2. And the second condition, that in fact it's isotropic over K itself, and therefore isotropic at every place. I don't have to make any specific. So this is the, well, now in simple case, you can actually formulate something more general. Namely, you don't have to demand that S be a finite set. You can actually formulate things without S being a finite set in general, but only in the simple case it becomes interesting because it's one sees easily if S is infinite. In the case of uniponent groups or tori, the CSG is unwieldy, it's infinite. It's easy to see what happens there, but it's no longer interesting. So it's only in the case when G is semi-simple, even S infinite is interesting. Now, one can formulate this. So we drop the assumption. That G is, that S, sorry, that S is finite. And then the Serre conjecture still makes sense. If S is infinite, of course, you're happy because automatically the conditions specified there will be satisfied, except S should be isotropic at all places. There's one more condition which one has put down. And take the case, yeah. So when S is the complement of infinity, all places outside the Archimedean places. Take this extreme case, everything possible. In this case, the question is, look at GK. This is same thing as what I called GOS. Makes no difference. GOS turns out to be GK. Because OS is K. You're inverting so. And then you're looking for subgroups of finite index. You can ask, in particular, you can ask for normal subgroups of finite index, or more generally for normal subgroups. Does GK have normal subgroups at all? That's the first question. If it turns out if G is isotropic over K, or now it is known that GK is simple modulo its center. This is the so-called affirmative answer to the Kneser-Tich conjecture. Kneser-Tich conjecture tells you if G is isotropic over K, GK is simple modulo its center. It has no normal subgroups other than central ones, which are necessarily finite. So we have an affirmative answer if G is isotropic over K. It's the same thing as the Kneser. By the way, the Kneser-Tich conjecture, it's a very long-standing conjecture. It was finally proved only about 15, 20 years ago. Not before that. It went on for a long time, and they proved it for all cases except two exceptional groups, but that was also settled some 15, 20 years back, something of that kind. Maybe less. But anyway, so this question, the CSG for this S is trivial, the same as affirmative answer to Kneser-Tich. I think the final lid on this conjecture was put by Gilles. Before that, a number of people contributed various things. For the classical groups to solve, mathematicians who were born in the 19th century already gave us solutions. For non-class, Kneser was among the people who proved a number of classical cases. And I think CTC Wall also contributed something in this direction. It's an unusual name to find in this context. Anyway, so a lot of things were done. The classical cases, it was all done long ago, but for the exceptional groups, some things were left and something was solved only in the early years of this century. Okay, so that is the Kneser-Tich conjecture is a special case of the Serre conjecture, if you like, in this context. Okay. Curiously, people did not look at the infinite case. I mean, when S is infinite, was not something which wasn't looked at for a long, long time. It's the first person to look at it in this fashion. The case when S is everything outside infinity was Margulis, in fact. Margulis, in fact, showed that if you take S, so D, a quaternion division algebra, and you look at SL1D, that is a set of elements of reduced norm 1 in D, this is an algebraic group. For this group, he proved, and then he showed that C, S is above. No, you should be careful here. Now take S to be the set of elements V, valuation, V is either Archimedean or, sorry, S should include, yeah, V is Archimedean or dV, D tensor kV, kV is the completion at V, is isomorphic to M2 kV. This happens for almost all V. So this complement of S is finite. That's the situation you're in. In this case, he showed that implies CSG is trivial. And then earlier on, for certain special subgroups of finite index, it was proved by Platonov and Rapinchuk that they are actually congruent subgroups. So specifically, they looked at the commutator subgroup of the arithmetic group of the maximal order in normal elements. I mean, normal elements in the maximal order, and then take the commutator subgroup. That works. It's something which they proved. And then Margulis went ahead and proved this very general result. This naturally can ask the same question with any division algebra, replaces by division algebra. And here D tensor KV is MR KV for some R, sorry, MR EV, where EV is some division algebra over KV and R is greater than 0. Look at the set of evaluations such that D tensor KV is MR EV, then CSG equal to 1. This result is due to, well, a number of people, various things combined, Platonov, Rapinchuk, then myself, and Sagev. The works of all these people combined yielded this result. So that is at the other extreme. Instead of S being finite, you're making complement of S finite. You can ask the question, this is a special set whose complement is finite, but I can ask, start from any set with complement finite, is the statement true? And that is true. That follows from some work of mine with a student who is here, Radhika, and also independently Gopal Prasad, Rapinchuk. In fact, you see, this is a case when the group is isotropic, anisotropic. If you look at SL1D is a group which does not admit any split torus. So, well, I'm almost running out of time. A few more minutes. Obviously, I'm not going to talk about any proofs. It's out of the question now, clearly. As I said, the one standard thing is that you always prove that the extension is central, that the congruent subgroup kernel, CSG, is a central, and then apply second cohomology criteria. And yeah. So the situation, the point is that for anisotropic groups, yeah, but let me also say that for anisotropic groups of type Bn, Cn, or Dn, one knows the CSG is either roots of unity or 1. That is known, even for anisotropic groups. That is due to the work of Kneser mainly, and then followed by Kneser's ideas. Kneser proved it for type B and C and D, and then for some exceptional groups. No, actually Kneser proved it for type for orthogonal groups, and then they were extended to other groups of type B and C and D by Rapinchuk, and also Tomanov proved it in some cases and so on. And maybe I'm missing out some people. For some exceptional groups, Rapinchuk, Tomanov, for all, so classical groups of type Bn was handled by Kneser, and Rapinchuk, Tomanov completed Kneser's stuff by including everything of type Dn as well as Cn. Actually, I had also an approach for proving the same theorem for the classical groups of type B and C and Dn. Anyway, so the type An was the one which gave the maximum trouble, and some recent advance has been made in the case of groups of type An, that is in the groups of type SL1D, D a division algebra. So the theorem which has been proved, which will contain these results of Sagev and as a special case, Margulis and Platonov, Rapinchuk, Sagev as special cases is the following. I'll make a definition. A set S of valuations containing K, containing infinity, is amenable, is de-amenable if the closure of K was the ideal group formed out of or rather let me write in A star is S is dense in a subgroup of finite index. If this happens, so the theorem is S amenable, S de-amenable, D division algebra of degree D, then CS GL1D is trivial. Well, it turns out de-amenable may look like a strange definition, but it turns out, for instance, that if S is a set of places where a certain Galois extension, where for a certain Galois extension, S consists of all elements whose Frobenius is a given element in the Galois group. It's a technical definition, unfortunately, can't be helped. But this is the new result, which is essentially same result, slightly weaker one, was also proved by Prasad Rapinchuk. And this result, as I said, is due to Radhika and myself. And there's the Prasad Rapinchuk theorem, which is slightly weaker than what we have. Well, this is all I have to say. I'm sorry I've not been very... Okay, thank you.